All right. Do you hear me well? Good. So, today I want to talk about some lessons I learned while building a tool based on LLVM. And a few words about myself. My name is Denisov. I work at PT Scientist GmbH. There we are doing some spacecraft software and spacecraft itself. And beside that, I'm using LLVM for several years. So if any of these topics are of your interest, you can just get in touch with me and we can chat. So the agenda is the following. These are some topics that are quite general enough, in my opinion, to be applied to any LLVM-based tool. And it includes like build system, memory management, and some pitfalls related to that. But I want to tell why am I talking about this, or like why am I credible to talk about that? So this is the project, my basically hobby project. It's called MUL. It's a tool for mutation testing. And if you want to learn more about the mutation testing itself, then I encourage you to either watch my talk from FOSDEM 2 years ago, or read the paper. You can easily find preprint, which is not behind paywall, if you're interested. The tool works on Linux, macOS, and FreeBSD, and it has another nice feature, in my opinion. So here I have a normal program, just normal executable, and I can run that. And the tool is also able to just work with this executable. Also, we've got a badass logo with the dragon, which also adds a tone of credibility. Before we start, I want to put a disclaimer. So I am an expert here, so you should follow my advice blindly. Unfortunately, neither of these statements is true, so take my advice with the big grain of salt, okay? So to have some framework in mind, I would like to kind of define what I mean by LLVM-based tool. So first of all, it should work with LLVM Bitcode, and it does analysis, processing, and maybe some transformations. So I think examples would be like compiler, for example, or obfuscator, or mutation testing tool, or anything else you can imagine. So the very first thing that, in order to build LLVM-based tool or just a tool, you need to have a build system. And lots of articles on the internet and documentation refers to LLVM config, and I think I wrote a couple of articles myself, and it was uneducated blog post. So this is how typically your compilation would look like if you use LLVM config. But there are some pitfalls. So these are C++ flags, right? They look legit, but first of all, if you use precompiled version of LLVM, then you will get no optimized flag and no debug. And also, you may get some flags or warnings that are specific to Clang. So, for example, you won't be able to compile your project using older Clang version, or, for example, GCC or some other compiler. Important point here that these flags, these are not the flags that you need for your tool, but these are the flags LLVM was compiled with. So there is a difference. So it's important to know, I think.
We fixed that in version 8.
There is a comment that it was fixed in version 8. We'll see. There are, I didn't finish yet. So let's see how much you fixed. So the second pitfall is libraries. If you want to compile, or if you need to link some libraries, some parts of LLVM, then you just call it like this, like libs, and enumerate kind of modules or LLVM parts of LLVM that you need. It works good so far, unless you have such a setup. It's really easy to get on Linux. So what happens is you have 2 LLVM versions installed, like in this example, 4 and 6, and they both have LLVM dilib provided. So when you compile it and link like this against, for example, LLVM support, you may eventually get this LLVM error inconsistency in registered command line options. I must admit I spent quite some time digging into it, trying to understand what's the problem, and I could not. And actually I was pointed out by a person on GitHub of the solution that if you have LLVM dilib on your system, then you actually should link against that, so dash LLVM. So to use properly the LLVM config libs, you would have to also check if there is a file or not, so it's really not convenient. Another problem, if you want to link some Clang libraries, then we faced that on Linux. So it works well on Mac, but on Linux there is a problem with the order of libraries. So you should specify them in very specific order. It's fine with LLVM, you don't have to take care of that. But with Clang, it's not, there is no Clang config, right? To the best of my knowledge. Yeah, so we had to do this kind of trick, and it's a very simplified version, so our build script was much bigger. So if you allow me to give a recommendation, that I would strongly insist you are on using CMake. So if you don't know what the CMake is, I also encourage you to read the documentation from an LLVM website. It's really good overview, and if you have zero knowledge, then you can get up to speed very fast. But essentially, CMake is, it has several constructs. It just builds, to create an executable, you need a list of source files, you need include, header search path, or includes, and you need libraries. So that would just look like this, typically. So how do we get that from LLVM, if you want to use CMake with LLVM? So CMake is, LLVM is coming with a great CMake support. It's really highly appreciated, the amount of work that was done for that. And it's really straightforward to use in the CMake. You just find a package, provide the name of the package, and it just works. Two important points here that the first one is path to LLVM. It's just an arbitrary name. I picked it for almost no reason. This is the one we force a user who wants to build our tool. They must provide this path. And we exclude no default path. Because again, if you have several versions of LLVM installed, and I think no one knows what happens and which version it will pick. So it's really not non-deterministic. Yeah, and the same applies for Clang. You can just use Clang libraries. So once you've got this done, you can just use LLVM includers. They are available, and also all the libraries from LLVM as you would use your own libraries in CMake world. Except you may get this problem again with the file, with the dilib. So the recommended solution that works, maybe it's not the proper one, but it works, is to check. So the LLVM exports a list of all the targets it has, and you just check if LLVM is there, then you link against that. Otherwise, you link against your preferred libraries. Okay, I think we are almost done with CMake, at least partially. So are there any questions so far? So side note, we have plenty of time, and I think my talk will not take 60 minutes, so feel free to raise a question, and anytime. Okay, the next point that we try to support several versions of LLVM. One of the reasons was that when we started, there was LLVM 3.9, I think, and eventually there was released LLVM 4, and we wanted to check if it works there, or if we should update immediately or not. And it was quite hard to have to support both things at the same time. And so we found an approach. So this is the one that is used in CLI or CLE. I don't know how to pronounce it correctly, sorry. So basically in your source code you have lots of if, def, and so on. So it works. They also support multiple versions, I think from 3.9 or 3.8 to 7 or something, so any version. But I find it kind of dirty approach, so I don't like that, and we took the other way. So basically, we provide just a bunch of kind of libraries that are gluing our tool to the LLVM itself, and it looks like this on the on the hard drive. So from the CMake perspective, then we just check. We take the LLVM version and we check if there exists a folder or a library that provides the glue for that version. Then we use that. Otherwise, we say that it's not supported. So yeah, again, it's a simplified example. You can find the full listing on the GitHub if you want to. Yeah, it's a bit more clever, I would say, there. So this is how it looks like a typical header, LLVM compatibility H in our case. So on the left side, there is 3.9, on the right side, there is 8.0. So they are almost the same. And if I want to, or if I would to classify what changes between versions, these are just three things: headers or your includes, types, as we use just type devs to use different types to work with renames, for example, easily, and just some APIs, some functions. So for the functions, we just create our own wrappers, and that works quite well. Yeah. In this example, so we actually don't have that much code, and there are two reasons or several reasons for that. One of them that we probably don't use that much of LLVM APIs. Another reason that API became stable or quite stable, at least those parts that we are using. And yeah, this is another part that we used WorkJet, and we spent, it was changing for good. Every version, like drastic changes, and it was really hard to support that. And I dig into it and was looking like how can we build some abstraction layer on top of WorkJet so that we have some stable interface. But after that, I just realized that WorkJet as well as MCJet is just a wrapper or just a layer on top of things like symbol resolver, memory managers, and linkers, static dynamic. So we just end up crafting our own layer on top of that called NativeJet. Straightforward, simple, bare minimum. By the way, if you're interested into Jet, today there will be a talk about Jet, something at Facebook. And tomorrow there will be a roundtable. So please join and we can chat about this topic. Another important point about supporting different versions and changing APIs. So there was a pitfall for 3.8. So the API, there is like clone function. The API itself didn't change that much, as one parameter is gone. But we've got some weird crashes, and it took some minutes to debug and to find what was happening. So actually, besides the API, also changed the semantics of the code. And there is simply no way to know that. So just be aware of that. So for sake of this example, clone function on LLVM 3.9 and higher, it puts the function into the same module where the original function resides, and before that it was just like dangling somewhere, so function without a module. Right. So far I was only talking about using CMake and building against a precompiled version of LLVM. That works quite well, and these are like trade-offs, pros and cons of both approaches, building against sources or against precompiled versions. So I think for a couple of years probably we were just using precompiled version and didn't touch sources at all, and suddenly we started getting some bug reports from a person who was porting it to FreeBSD. It turned out that in several places we violated LLVM constraints. So basically we started hitting assertions on custom-built LLVM. So assertions are disabled in precompiled version, and you will never know about that, because in our case it worked somehow, maybe just by coincidence. But it's important to have assertions as well. So we decided also to not only support precompiled LLVM versions, but also support built against sources at the same time. And it's a bit less tricky, or a bit more tricky, sorry, a bit less trivial. So how we do that? Basically, we just check if there is CMake list txt in the path to LLVM. It means that we are building against sources. And then we just add LLVM itself as a library. So we own LLVM. And it's very important because other approaches, they suggest that you put your code in tree, for example. And it's really not, in my opinion, not that straightforward to support in the long term, unless you have some like big team with many people and great resources. However, in this case, we don't have things like include years and LLVM version. But yeah, with include years, it's really straightforward. We can just read a property of some of LLVM library, and we'll get those include like header search paths, and it just works. I think it may not be necessary in the recent version because of CMake capabilities, but I'm not sure if that worked in some older versions. So just try it out if you want to. Yeah, for LLVM version, the most straightforward approach, we just use regex to parse CMake lists to find the version definition. Very fragile, and but it works. So, okay, by this time we're definitely done with CMake and want to talk a bit about memory management, or rather pitfalls. Yeah, there was a question, sorry. Could you repeat the question?
Are you running a performance problem and try to use profile-guided optimization?
We were running into performance problems, but they were not caused by LLVM itself, but by our implementation. So we were instead improving our implementation and measuring everything. I will get to this to this topic, and we'll show some numbers. But we didn't try profile-guided optimization. Yeah. Okay. Yeah, a bit of code. So who knows what's wrong here? Any ideas what could possibly go wrong? Okay, this code will may crash or may not crash because what happens here, we create a vector of modules and unique pointers to modules. Then we create an LLVM context. Then we load a module into that context, and we store that module into that vector. So I think like if I look at the code, I see that we own the modules, and they are owned by this standard vector. But that's not the case. So what happens, in fact, then when this code executes and destructor is called, first LLVM context is destroyed, and it deallocates all the modules, and then vector of modules also wants to deallocate those, and you get double free. And I don't know how it works, and if you know, please send help. The solution is actually easy. You just swap the lines, but yeah, you need to know about that and keep that in mind. Otherwise, you will find yourself 3 a.m. debugging some memory corruption issues. Important point here that besides the APIs, I think the modules are owned by LLVM context. And it's important because we hit another problem. So we had just pseudocode. In our case, it was like running a loop for 1,000 modules. We create a copy of a module, do something with it, and that's it, and just throw it away. So we create module in the local scope of the for loop, and assumption was that it's just deallocated at the end of the scope, right? It worked great, no problems, unless we run it on a 32-bit system where we have limitation, like with 4 gigabytes of memory, or roughly about that. And we just crashed with out of memory. So it turns out that the modules, they are not deallocated. They just stored in the LLVM context, and they leave with you unless the LLVM context is deallocated. Another problem that from like UX or UI perspective, if you do it this way, then at the end of the program, when LLVM context deallocates, it frees up all the memory, and you see, like as a user, you see the program just does nothing for quite a long time. yeah, solution is again straightforward. Just create some local context that will be destroyed after each loop iteration. Okay. Yeah, question.
So is the problem there that load module returns just a module pointer, not a unique pointer?
It returns unique pointer.
It returns a unique pointer and it still doesn't get freed?
Yes.
Okay.
That's what I'm saying, that I don't understand how it works, really. I thought I know something about C++, but not anymore. Yeah. Okay, my favorite topic is parallelization. So they just advise, if you want to parallelize LLVM or anything, you shall not use passes, right? That's it. If you don't do that, you're good to go. And yeah, let me elaborate on that. Few points or few classes in LLVM that are not thread safe. You just wrote them here. They are they're the most used in our context. You may have some different classes. So target machine and LLVM context, they are not thread safe, and therefore, if you do anything with just an instruction, you change the name of an instruction, it also affects, or it may affect LLVM context. So you may hit some not deadlock, but data race, and some nasty problems. Yeah, I think LLVM tools, they are really great for a thing called, fair parallelization. It's where you have, let's say, 20 tasks, and you have 5 cores on your machine, and you just split them evenly, and it just works faster. But LLVM infrastructure doesn't really support that, so you would have to do this kind of on your own. And yeah, this is the example. So here, just assume that we have 3 modules, and we have two threads. So we can somehow split this work. So we put 2 modules on the first thread and the third module on the second thread. And it's important that each thread should have its own LLVM context. Otherwise, you will get into the trouble. Or, of course, you can overcome that by adding some locks and so on. But what's the point then of parallelization if you're doing lots of locks and mutexes? So here then, for analysis, if you're just reading something, trying to get some information from, let's say, functions in this example, then you can take all the functions and split them evenly between 2 threads. It will speed up things a lot. But when it comes to transformation, then all the transformations, they should live in the same thread of the LLVM context they were created in. Otherwise, you'll get into trouble. So here, I think you can see the bold arrow. So for transformation, it should not escape the boundaries of its thread. Yeah, and why I'm saying that you should not use passes, because the design of passes in LLVM, they kind of incentivize you to use, to combine analysis and transformation. And if you split those, it's easier to test, because you can just test analysis and just test transformation. And again, you get the performance improvement. These are some numbers. They might be different for your use case, and for our use cases, it also depends. But this is the idea that with analysis takes more time, because let's say you have 1,000 instructions and you need to find some of them to modify some of them. And you need to go through all of them, like all the 1,000. But you need to transform only 10 of them. So in the first pass, you just gather all the instructions you want to do something with them, and then you just transform. You can see the performance improvement. So the bar on the left, blue one, it's sequential execution without threads, without parallelization, and on the right, it's with parallelized. But of course, you should always measure, because maybe it doesn't help, because in our case, just to get all the modules, I think these numbers are taken probably from LLVM itself. So we are loading LLVM and doing some stuff with it. So it may not make sense to actually do that. So yeah, it's up to you to decide. And in our case, like total execution time, if you compare that to just the split of analysis and transformation, it doesn't make any sense to spend an effort. But we still do that because it's much cleaner. Another important point about parallelization, that if you're working with Bitcode and if you work with some big programs, as for example we do with LLVM itself, so we JIT compile ADT tests, the test suite for abstract data types, and I think on my machine it was taking, like just to JIT compile the whole thing, it was about 2.5 gigabytes of RAM, and I have 8 cores, but I have only 16 gigabytes of RAM. So when I run the JIT and each thread instantiates the own copy of JIT program, it just exceeds the RAM and the program starts swapping, and it's actually faster to run it on 4 threads or on 4 cores than on 8 cores. So that was, I mean, that's obvious, right? If you think about that, but it was not obvious to me when I faced this issue, like what goes wrong. Yeah, next topic is getting Bitcode. I think once in a while, maybe once per month or once per 2 months, there is a post on mailing list asking like, how do I do that? And recently, I've seen like 3 times somebody, like 3 people, different person asked about this question: how do I get Bitcode for a program? And if you search on the internet, there are a bunch of questions on Stack Overflow. Not all of them answered. So there is really a demand for that. I think the first advice for everyone is to use a whole program LLVM, but I want to discourage you from doing that because as far as I know, again, correct me if I'm wrong, it gives you just one LLVM module for the whole program. It works, but you cannot parallelize them, and the tool and everything is just getting sloppy and slow. Instead, there are some other ways to do that. So this is kind of pipeline, compilation pipeline. If you call Clang with emit LLVM flag, then you get just, instead of an object file, you get LLVM bitcode or LLVM IR. And you don't get an executable. The second option is to call actually FLTO. In that case, instead of object files, you will get, LLVM IR or LLVM bitcode, and you will also get executable, like normal executable. That works quite well. We use it a lot, this approach, only if your build system is good enough. So, for example, with CMake, you get separate object file for each source file, and that works. You can get bitcode. But if you have some handcrafted shell script makefile-based system that just takes a bunch of source files and as an output gives an executable, there is just no intermediate step. There is no object file stored on disk, so you cannot use the bitcode. So there is the third approach, my favorite one, embed bitcode. So in that case, instead of object files, or you still get object files and executables, but they also contain bitcode. And this is how this thing worked on the demo. So I'm not sure if you can see what's written there, but basically the tool extracts bitcode from the executable and just starts running. And comparing to other tools that I've seen on the market, so to speak, it's really a huge improvement in UX. So to do that, Jonas, I will not pronounce his last name because I don't want to make a mistake. So he wrote a great tool called LeapEBC. EBC stands for Embedded Bitcode. So what it does, it basically extracts bitcode from an executable and it can store it locally on disk. So I made a fork and extended it to extract bitcode into memory so that there is no I/O step, basically. I still hope that I will at some point submit those patches so that the main repository will get all these features. But if you're interested, meanwhile, you can look at my bad code there on the GitHub. Yeah, this is how it works. You just provide CMake flags, C, C++, embed bitcode, and bam, you're done. So it's really, really straightforward. Okay, Next topic, multi-OS support. So as I mentioned, it works on FreeBSD, macOS, and Linux. And to do that, just like 2 words, Vagrant and Ansible. That saves a lot of time. So if you're not familiar with those tools, I highly encourage you to take a look at them, even if you don't want to build any LLVM-based tools. It's like just really great instruments. So what Vagrant does, it's basically a manager of virtual machines, right? In a nutshell, like simplified description. So we have a Vagrant file that just describes some machines that we support. In our case, it's Debian, Ubuntu, and also FreeBSD, macOS, and so on. So if I need to debug some issue on Fedora, for example, and I'm running on Mac, I just create the virtual machine. It's completely automated, and then I use remote debugging facilities of my capabilities of my IDE to do that, and I'm having just native experience. So it's really straightforward. Another point, the Ansible here. So each virtual machine. So Vagrant just creates the virtual machine, but then it uses Ansible to do all the setup on it. So these are just like high-level tasks that what it does for us. It installs all the required packages, downloads LLVM version that we need or sources of LLVM, builds the tool, and runs all the things. The only difference between Linux and Mac and different Linux distros like Fedora and Ubuntu, Debian, the list of packages, just names are different. And besides that, we share all the steps between all the platforms. It's really straightforward and easy to maintain. Another great part of Ansible that you can just run it locally on your machine, or in our case, we do it on CI. So basically we just reuse as much codified infrastructure as possible. And it really helps. I think a week ago or something, I released the first version of the tool, and it was really, really straightforward to build all the packages for different operating systems using Vagrant, Ansible, and CMake and CPAC. What I did, like Sunday morning, I think, I just ran the script. My machine at home went off, and when I was back, I had all the packages. So it's really easy solution. Okay, I think it was a bit faster than I expected because this is my last slide. I didn't touch the topic of testing because I was afraid. I wasn't sure if I can find the right way to show how that works. But just a few things to mention that you absolutely should use C Smith or NC reuse to test, to make sure that your tool is robust. So we don't have it on our project yet, but on other commercial projects, I used it, and just within 5 minutes with SysMid, we found some violations of LLVM constraints caused by our tools because developers had some wrong assumptions about how it should work. But anyways, are there any questions?
Let's thank our speaker. So, any question?
Did you explore other build systems besides CMake and LLVM config, or did you just immediately go to CMake after you realized that LLVM config wouldn't do it for you?
Well, yes and no. So I know that there are some other systems, but LLVM provides great support for CMake. So that was the main decision force basically behind. And also, I don't know if other systems they can provide can generate projects like for Xcode or Visual Studio, for example. So CMake was just default option. Thank you.
Have you tried on other operating system like Windows?
I would love to try that actually, and I think the tool can work on Windows as well, but I just don't have access to Windows machine. I'm very, very sorry about that.
Okay, thank you.
Yeah.
Hey, thanks for the talk. Just a note on the context and modules thing. There is this great thread-safe module construct that Lang Hames added recently to exactly approach this problem so that every module has its own context. So that's also the solution in org v2.
Thank you. Yeah, it's good reference. I will take a look.
Any more questions? Doesn't seem so. Let's thank our speaker again.
Right.